So today we are going to finish up our discussion on effectively how to implement current sources in integrated circuits. First of our advanced current sources that we are going to talk about is the Widlar current source. And I'm only going to talk about the BJT representation of these three current sources today because their analysis is significantly more difficult than that of the MOSFET. For the MOSFET, you can practically do the analysis by inspection. So I'm going to kind of leave that to you guys so that we can get through all of this in one day. Okay. So the Widlar current source looks like this. We have our reference current, Iref. And then we have a diode connected BJT. On this side, we have a not diode connected BJT on this side. Here is our current I copy. Let's call this guy Q1. Let's call this guy Q2. So far it looks exactly like a simple BJT current mirror. Here is the big change. We degenerate the emitter of only one of our BJTs. Okay. So this is the Widlar current source topology. This was developed pretty early on in the days of integrated circuits as a means by which to develop small, stable copy currents using minimally sized resistors. Okay, so in the burgeoning days of integrated circuit design, our reference current wasn't supplied by a current source. It was literally a resistor. Current through the resistor biased the rest of this network. And this particular topology allowed you to get away with using a reasonably small resistor here and a pretty dang small resistor here in order to get the same results as something that would take hundreds of kilo ohms of resistance to generate. Okay. This is actually the current source that's used to bias the differential pair stage of a 741 op amp. Even to this day, what they used to do. Okay. So it should be fairly obvious here, but there is a base emitter voltage, VBE1, across our transistor Q1, establishes its bias point. And there's a base emitter voltage, VBE2, across the base and emitter terminals of transistor Q2. And these guys are obviously not the same, which is significantly different from what we've looked at in these past several lectures. Okay. So by inspection, we can observe that our reference current, Iref, is beta plus 1 over beta times the collector current for transistor Q1. And I'm going to label that current here. So let's call this guy IC1. So effectively, the reference current is IC1 plus IB1, which added together just looks like the emitter current, which is where I'm getting this relationship from. Okay. So from this, we can say that this is simply beta plus 1 over beta times IS EXP VBE1 over VT. And what I'm going to do now is I'm going to solve for VBE1. Right. So solving for VBE1, we'll find that this is VT times the natural logarithm of IREF over IS times beta over beta plus 1, which is the same as VT natural log IREF over IS plus VT natural log beta over beta plus 1, where we are going to say that that natural log of beta over beta plus 1 term is approximately 0, which should be true if beta is large, okay? So this is actually one reason why this particular configuration doesn't get a lot more application than what we are going to talk about later on in this class. We have a high dependency on beta to establish our operating point here, okay? So under the assumption that beta is very large, so that beta over beta plus 1 is effectively 1. Now let's look at our copy current. So I copy is simply IS EXP of VBE2 over VT, where I've made another assumption here. And that assumption is that transistors Q1 and Q2 are perfectly matched such that they have the same saturation current IS. Okay. Rearranging this guy, we find that VBE2 is VT times the natural logarithm of I copy over IS. And what I'm going to do now is I'm going to take the difference of these two voltages, okay? So VBE1 minus VBE2 is going to give us VT natural log of IREF over IS minus VT natural log of I copy over IS, which simplifies to VT natural log of IREF over I copy. Are we okay with the manipulation of natural logarithmic functions here? Everything seem okay? All right. Now what we're going to do is we are going to develop an alternative expression for VBE1 minus VBE2 by applying Kirchhoff's voltage law around this loop, the bottom half of the circuit, okay? We can see, applying Kirchhoff's voltage law, that VBE1 minus VBE2 is just going to be RE times the emitter current of Q2. which is beta plus 1 over beta times I copy. And we can now put these two expressions for VBE1 minus V2, set them equal to each other. And what that gives us is beta plus 1 over beta multiplied by I copy RE is equal to VT natural log of IREF over I copy. Or since beta plus 1 over beta should be very close to 1 because of the assumption that we made earlier, I copy times RE is approximately VT times the natural log of IREF over I copy. So this circuit is used to take large-ish, by that I mean on the order of milliamp input or reference currents, and convert them to steady integrated circuit biasing currents on the order of tens of microamperes. Okay. So it takes largish currents and makes them small and stable to bias microelectronic circuits. All right. And that's what this transfer function tells us. Now, one of the principal advantages of the Widlar current source is that it has a higher output impedance or higher output resistance than a simple current mirror alone. So we're going to look at that detail real quickly. Or am I okay to move on to a separate page? All right, so if I look at the small signal model of this guy, here on the left, I have my diode connected transistor. So this is the collector terminal of transistor Q1. Over here is the base terminal of transistor Q1. And then down here is my ground. So this is my emitter. Over here on the right-hand side, I'm going to draw what's going on with transistor Q2. Here is RE. Let's see, this is the base of Q2. This is the collector of 2. Since I'm finding my output resistance, I'm going to apply a test voltage source, which I'm going to call V out. I'm going to determine this current I out. And one last thing that I need to do here, my bases are tied together. Okay, so let's start with, are we in accord that this is what our small signal model should look like? Let's start there. This is the emitter of transistor Q2. Anybody see any problems or anything? All right, so to aid in our analysis, I'm going to put a vertical line here bisecting the circle. Okay. What does everything to the left of that vertical pink line look like? So let's talk our way through it, okay? We have a diode connected BJT. So this current source, GM1 VBE1, looks like a resistor having a value of 1 over GM1, right? Because there's a linear relationship between the voltage drop across that current source and the current flowing through the current source, so we can treat it like a resistor, okay? So we would have R01 in parallel with R pi 1 in parallel with 1 over GM1. Are we okay with that? We've done it before, so it seems reasonable, like we should be able to do it again. Under the assumption that 1 over GM1 is smaller than R pi 1 and smaller than R naught 1, we can treat everything to the left of that pink line as just 1 over GM1. Because we know that whenever we have resistors in parallel, they're going to be smaller than their smallest contributor, right? All right, now we're going to make yet another assumption. The assumption that we are going to make is that for our matched transistors, R pi 2 should be larger than 1 over GM1. Right? Doesn't seem wildly unreasonable since we just assumed R pi 1 was much larger than 1 over GM1. So effectively, we are saying, if we go back to our original circuit here, all of those assumptions that I just made, all that really says is this circuit is used to establish the bias point of this circuit, which is exactly what current mirrors do, right? So this guy gives us the DC operating point of this guy. So we're treating everything to the left of that pink line effectively as if it were grounded. It's not contributing much, if anything. From there, our analysis is pretty straightforward. Now, realistically, we don't even have to do it. What I mean by that is if this is ground and we're looking into the output terminal, we see the output of a current source that has a emitter to generation resistor, right? Which we've dealt with before. More formally though, we can say that the voltage VBE2 is negative I out times RE in parallel with R pi 2, or I'll explain that for those of you who don't quite see it, okay? This current I out flows into this node C2, splits up, recombines, and then sees a resistance of RE in parallel with a resistance of R pi 2 when we say everything to the left of the pink line doesn't contribute. So I out is flowing into the negative polarity terminal of VBE2, where VBE2 is just the voltage drop over RE in parallel with RI2, which is summarized. Y'all catching what I'm throwing? All right. So if we apply a Kirchhoff's voltage law loop around this portion, what we will have is that V out is equal to R naught 2 times I out minus GM2 VBE2 minus VBE2. If we substitute in our relationship for VBE2, this becomes R naught 2 times I out plus I out times GM2 RE in parallel with R pi 2 plus I out times RE in parallel with R pi 2. And from this, our output resistance, V out over I out, is 1 plus GM2 RE in parallel with R pi 2, all multiplied by R naught 2, plus RE in parallel with R pi 2, or approximately 1 plus GM2 RE in parallel with R pi 2 times R naught 2. The reason why I'm choosing to use this form is because this allows us a direct comparison between the output resistance of this configuration, the Widlar current source, and a simple current mirror, which would have an output resistance of just R naught 2. So choosing RE wisely, we can apply a significant boost to the output resistance using this configuration, which should not be surprising because that's literally the point of degenerating the emitter, which we talked about when we first began talking about current sources. So this is our Widlar current source. More of a historical curiosity at this point than being widely used, but it is mentioned in the textbook, so I figured I'd talk about it. Okay. It can also be implemented using MOSFETs, but again, the analysis there is actually much, much easier. All right, how do we feel about this guy? Good enough to move on? Okay, great. The next one that we're going to talk about is a simple cascode configuration. So for our cascoded current mirror, where this is our current IREF, we would have the following case. Where effectively we just have two current mirrors stacked on top of each other. So we cascode the current mirror formed by transistor Q1 and Q2 with an additional current mirror formed by transistors Q3 and Q4. Right? Our output resistance, our out, we are not going to solve for because it's the exact same thing as the cascode current source that we dealt with earlier on this week. So with these particular labels for our transistors, it's going to be approximately 1 plus GM4 R02 in parallel with R pi 4, all multiplied by R04 plus R02, oh goodness, in parallel with R pi 4. And so we can see that we're applying an additional 1 plus GM4 times R02 in parallel with R pi 4 of output resistance, or that many times what we would have with just a simple current meter, okay? So obviously we get a large output resistance because that is literally the purpose of cascoding. So what we're going to talk about now is the ability of this device to generate a copy current based on I reference. Okay. So what we should observe here is that this voltage VBE1 is the same as this voltage VBE2. Which in turn means this current IC1 is equal to this current IC2, and this current IB1 is equal to this current IB2. I'm going to go ahead and label a couple of more currents here that we're going to use in our analysis. So this will be IC3. This will be IB3. This guy here is IB4. This guy here is IE4. And this guy here is IE3, and I believe I've got everything like, yeah. Okay. So I'm going to call this node X, this node Y, and this node Z. We're going to wind up applying KCL at all three nodes and then algebraing our way into a relationship. So KCL at node X, all right? So the current that's flowing in is a current IE3. And the current that is flowing out of that node is then IC1 plus IB1 plus IB2, where IB1 and IB2 can be expressed as IC1 over beta, right? Because we know that IB1 is just beta times smaller than IC1. IB2 is beta times smaller than IC2. And IC1 and IC2 have to be the same because those transistors Q1 and Q2 have the same base emitter voltages. So IC1 times beta plus 2 over beta is what IE3 looks like. Are we okay there? All right, now we're going to apply KCL at node Y. Where this one's fairly straightforward. IE4 is equal to IC2. Nothing more difficult than that. And we're going to play around with things just real quick here, right? So obviously we can say that IC2 is equal to IC1, so we're going to make that substitution in a moment. Another thing that we can say is that IE4 is beta plus 1 over beta times I copy the output current that we're looking for. Because IE4 is just the emitter current for Q4, and I copy is just the collector current for Q4, right? So that gives us beta plus 1 over beta times I copy is equal to IC1. And we'll wind up substituting that into here in a few moments. But before we do that, let's go ahead and play around with a couple of things. All right. So finally, KCL at node Z. So we can see here that IREF is IC3 plus IB3, which is simply IE3, which we already know. So IREF is IE3 plus IB4. All right. So IB4 is just I copy over beta. Actually, let's do some substitutions here. Okay, so for IE3, I'm going to substitute in IC1 times beta plus 2 over beta. And then to that, I'm going to add IB4, which is just I copy over beta. Now I'm going to substitute in my relationship for IC1. So that's going to look like beta plus 1 over beta times I copy times beta plus 2 over beta plus I copy over beta. And grouping things together, this is going to give us I copy times beta plus 1 over beta times beta plus 2 over beta plus 1 over beta, or I copy times beta plus 1 times beta plus 2 plus beta all over beta squared. And from this, I copy is IRF times beta squared over beta plus 1 times beta plus 2. So we have a copy current that is going to be slightly smaller than our reference current, right? Seems to have a pretty strong beta dependency here. If, let me pull that back down. So for beta equal to 100, I copy over IREF. This is our current transfer function, is 96.135%. So it's a pretty good copy. 96% of the signal survives. When beta is equal to 50, I copy over IREF. Comes out to be 92.524%. So an appreciable reduction of about 3.5%. Lastly, if beta were equal to 10, I copy over IREF. Comes out to be 70.423%. Okay. Giving you these values for different values of beta to illustrate the dependence of this guy's ability to copy that current depends largely on the beta value. Okay. The next circuit that we are going to analyze, the Wilson current mirror, rectifies this problem. Yes. All righty. So if we look here at node Z, current flowing in is IREF. The currents flowing out are IC3 plus IB3 plus IB4. We good there. IC3 plus IB3 is IE3. Yep. All righty. Let's see. We got 25 minutes left. You guys might have to trust me on the output resistance of this, so that this doesn't drag into another day. All right, BJT Wilson current mirrors. So the Wilson current mirror scheme looks like this. Here we have our reference current, IREF. And it supplies the base current for a transistor Q3, which is where our copy current is being produced. Down below this, we have a current mirror. Call this guy Q2. But we don't have quite the situation that we would expect. So this circuit utilizes negative feedback. So we have this reference current supplying the base current, which in turn supplies the current flowing through Q2, which in turn establishes the current that's flowing through Q1, which is subtracted from our reference current. That's why we have a negative feedback configuration. Okay, we got some interesting stuff going on that we can't talk about too much because we don't really know a lot about negative feedback amplifiers yet, but that's coming in the third portion of this class. So a few things here. Down here at the bottom, VBE1 and VBE2 are the same. Which again means that IC1 is equal to IC2 and IB1 is equal to IB2. So I'm going to go ahead and label those currents. So here we have IC1. Here we have IC2. This current is IB1. This current is IB2. While we're at it, I'm going to go ahead and label the rest of the currents for transistor Q3. So here's IE3. And here is IB3. I'm going to call this guy down here node X, this guy up here node Y. What's up? Sorry, all of these should be NPN, so I'll draw that arrow there. Thank you for reminding me. Thank you. All right, so our analysis here is going to be much the same as it was for the cascode. We're going to do our analysis at node X first, and we're going to follow it up with Y and do a little bit of algebra. Okay. So KCL at node X tells us that IE3 is equal to IC2 plus IB2 plus IB1. We know that IB1 and IB2 are equal, and we know that IC2 can be expressed in terms of IC1 because they're equal. And so what I'm going to do here is I'm going to manipulate the left-hand side. I'm simply going to relate this current IE3 to our output current I copy by saying IE3 is the emitter current. So it is just beta plus 1 over beta times I copy. And this is going to be equal to IC2 plus 2 IC2 over beta, which is the same as IC1 times beta plus 2 over beta. So to be clear here, IB1 is IC1 over beta. IB2 is also IC1 over beta. When I combine those two together, I get 2 IC1 over beta. And then I have a beta over beta IC1, which is how I get beta plus 2 over beta. We okay with that? We did the exact same thing in the last example, by the way. All right, so finally here, I'm simply going to manipulate this and I'm going to express IC1 to be I copy times beta plus 1 over beta plus 2. So I'm just moving this ratio from the right-hand side of the equal sign to the left-hand side of the equal sign. Actually, I think technically I moved this one, the other one. All right, how are we feeling thus far? Anything too wild or crazy? All right, now we're going to apply KCL at node Y, which is simply IC1 plus IB3. So that's going to give us I ref is equal to IC1 plus IB3, where IC1 is I copy times beta plus 1 over beta plus 2, and IB3 is I copy over beta. Grouping our like terms together, this looks like beta plus 1 over beta plus 2 plus 1 over beta, which is the same as I copy times beta plus 2, excuse me, beta plus 1, plus beta plus 2 all over beta times beta plus 2, and therefore I copy is IREF times beta plus 2 over beta times beta plus 1 plus beta plus 2. So this is our current transfer function effectively. And now what I'm going to do so for beta is equal to 100, I copy over IREF is 99.980%. So we have a nearly identical copy currently. Okay. For beta is equal to 50. I copy over IREF is 99.923%. So that's a pretty appreciable change in beta and a very small change in the error. And then finally, with a beta as low as 10, I copy over IREF is 98.361%. So for this Wilson current mirror, we see an appreciable improvement in the current copying capability of the circuit, right? These figures are all a few percent higher, and it's like 20-something% higher in the case of beta is equal 10. So we can see that this guy does a much better job of copying things. Now, without going through the derivation, just because I don't want to waste you guys' time on 3 more pages of notes when we have 10 minutes of class left. The output resistance of this guy, let me circle back here. R out. The derivation for this, by the way, is in your textbook. Comes out to be R0 3 times 1 plus GM3 R pi 3 over 2 plus 1 over twice GM2. So it's effectively this thing in parentheses times as large as R0 3. So we do still absolutely get a increase in the output resistance, but it's not as large as we would have seen from the Cascode. So that's the trade-off there. Practically speaking, you're either going to wind up using a Cascode or a Wilson, and it depends on whether you value output resistance higher than its ability to directly copy the reference code. So whichever one you need more is the mirror that you should use. All right, that's enough out of me for today. That is GM3 here, GM2 here. But since all of them are carrying effectively the same collector current, they're all roughly the same anyway. Most cases you would neglect this term because this guy is going to be so much larger than this guy. Logan.
Have you been able, I haven't looked, have you been able to upload some YouTube videos?
They're all up except for today's. I've been on my getting shit done.
I have not.
So is this purely just data independent of our system?
Yeah, effectively. So if we have process variations that cause a lower in beta, we still get a fantastic mirroring ability here. The trade-off there, though, is our output resistance isn't quite as high. So we get really good copy currents, but when we connect this to something else, our gain isn't as high.
Is it harder to get high betas?
It really depends. So if we had a discrete sampling of transistors that we bought, you'd be willing, the beta would probably range from 50 to 100, and it'd be all over the place in between those things, right? So this guy is really good for saying, don't care about beta.